Hi, and welcome to this video. Today, my team and I will be presenting to you our climate sustainability project. This project was based on the paper Is a Trillion Trees Enough? By Cedric Menage and Michalis Vlahos. The aim of our project was to first replicate the main findings of this paper. And this paper essentially examines the effect of planting 1 trillion trees on the planet on the global average temperature to see if tree planting, specifically in the Sahara Desert, is the way to go to mitigate global warming. And is a trillion trees enough to reach the 1.5 degree warming target that was set during the Paris Agreement? We start with what we call Task A, which is replicating the Python code that was provided by the paper and translating it into the Wolfram programming language. This task includes importing the data and the all-important step of cleaning and arranging the data so that it makes it usable for our modeling. And this step yields the basis results of the study. Next, Task B goes slightly further by including the albedo effect of planting trees on the temperature. And additionally, Task C adds water cycle effects, but we will explain those more in detail in just a moment. And before last, we also added an extension which examines the potential temperature decrease that can be achieved if, as a global population, we were to change our dietary habits. And how would this support the fight against climate change? And finally, we conclude by providing our solution. Let's now take a look at the code.
We first had to gather the data, but the CO2 data was divided in two up to year 1958 and then until 2020. We cleaned it, and then based on the CO2 levels per year, we performed a quadratic regression. We actually performed different models, and we found that the quadratic regression was the one that performed best. We can actually see the results and see how the predicted data follows very well the data from our data sets. Then, using the predictions, we performed another quadratic regression, but now with L2 regularization, also called a ridge regression. And we can see over here below the results. We can see that by year 2050, the predicted temperature is close to 2 degrees, which is above the recommendations of the IPCC, which is to keep temperature below 1.5 degrees by year 2050. Then, as in the paper, we made a prediction what would happen if we plant 1 trillion trees. We first consider that 1 trillion trees sequestrate around 107 gigatons of carbon. So we distribute this amount of carbon logarithmically over 30 years. And then subtract the absorption to the predicted temperature. And we see that by year 2050, the predicted temperature is now 1.8, which is below the previous predicted temperature of 2 degrees. Next, we also try to model a realistic decrease of gas emissions based on the Python notebook of the previously mentioned paper. And this decrease is now performed linearly over the predictions from 2020 onwards. And we see that the predicted temperature on the year 2050 is now even lower. Finally, we wanted to show how the temperature of the planet would change as we plant from 0 to 3 trillion trees. For this, we consider a sequestration rate of 75 gigatons of carbon per trillion trees, which is the median of the lower level and the which is 42, and 107, which is the highest, the higher level of predicted gigatons of carbon per trees. And we can see that the predicted temperature is getting lower as the number of trees rises.
In this part of the project, we were searching to include the albedo effect on the global average temperature. We can see on this map that the desert albedo and forest albedo differ quite a bit. Thus, by planting forests in the desert, we create a surface that doesn't reflect light as much and has a higher contribution to heating. To model this, we use the Stefan-Boltzmann law. This law indicates the negative relationship between albedo and equilibrium temperature. we essentially extract the albedo factor from the fraction in order to calculate this factor that pre-multiplies a constant which is composed of luminosity and fixed distances. And we find that this factor jumps from 0.915 to 0.916. After performing some mathematical operations here below, we find a relationship between the temperature in Kelvin before and after the albedo change. We thereafter take this to the data and perform this transformation on the predicted temperature from 2020 onwards, which is when we start planting the trees. And we can observe here that the albedo significantly increases the temperature curve, and that we reach a temperature of approximately 2.3 degrees by 2050. We also see that this curve is discontinued, which is to be expected as we transform the last part of the data and left the previous untouched. In order to amend this, we can use a linear progression, which helps us account for a gradual change in temperature. This is also more realistic, as it takes several years or even decades for trees to fully grow and have their full effect. Upon doing so, we get a progressively smoother prediction line, depending on the number of years we choose to use for the linear progression. Next, we add the sequestration effect. So obviously if there's trees, there is also the albedo change and the sequestration, whereas in the previous part we omitted the sequestration just for simplicity in modeling. And we see that upon considering the interaction of both effects, unfortunately the temperature increase is still well above 1.5 degrees, but is of course a little lower than our previous estimate, so at around 2.1 degrees.
The last part of this project is the water cycle. Before going deeper into the model, I'd like to explain why is the water cycle of trees so important. Of course, we know, and we've seen previously, that the CO2 effect of trees, the CO2 capturing effect of trees, is quite important. But the water cycle can also have tremendous effect on our climate system. For instance, trees are known to increase the concentration of atmospheric water, which can have a good cooling and a bad warming effect. The trees can also participate in reducing water-related disasters, for instance, such as floods. The water cycle of trees also allows to protect the surface from solar heat, solar radiations, which can have a very important effect on different ecosystems, especially in big forests. However, there are also quite significant bad effects of the tree's water cycle. Perhaps one of the main is the blue paradigm shift, which describes the fact that upon planting trees, more water is retained in the ground, and therefore less flowing water, blue water in this graph, is available, for instance, for human use, which might prove problematic. On top of that, we know from the albedo section of this project that trees can have a heat trapping effect, especially when compared to highly reflective surfaces such as sand in the Sahara Desert. An important phenomenon of the tree's water cycle is the transpiration process. This process describes the groundwater that's captured by the roots of the tree and then re-emitted into the atmosphere through the pores of the leaves. This allows to have an easier modeling approach, which can be used to explain part of the water cycle effect on the temperatures. So we first developed a water cycle model, a first attempt at it that proved unsuccessful. So I'll quickly go through it to give you a brief overview, and then we will go into our actual model. This first attempt was based on a paper. This paper had found that trees in UK cities could have a net cooling effect, and found the power retained by those trees on this figure, on this table. Using this average cooling effect, we used calorimetric equation to quantify how much it would reduce the temperature of the atmosphere. This approach, although very convenient, had the downside of relying on many assumptions, one of those being the time span over which the trees would decrease the amount of power in the atmosphere. Because of that, the result we find would differ greatly depending on the time span we would look at, and would not prove reliable. To solve this problem, we decided to build a new water cycle model from the ground up. This model is based on these two papers and these two main figures. Figure 2 here shows a simplified model of Earth's radiation system. You can see here the incoming solar radiation. G here represents the radiation emitted by the Earth, considered as a black body, to simplify calculations, of course, and then the result of an infrared absorbing layer from which a fraction is sent back to the surface, called h. This model then uses, to do this model, we then added the effect of trees. This effect was calculated using this first figure, from which the latent heat, this value represents the latent heat of the planet as a whole. So to find the value that would be created by our trillion trees, we reduced the assumption made in the albedo part of this surface required to plant a trillion trees. With this surface, we could calculate the fraction it would represent over the surface of the planet as a whole. Doing this, we could find the effect of trees evapotranspiration, which would be, of course, much smaller than the total flux of the whole planet. Doing this and doing a couple of assumptions, the assumptions were all based on the second paper, Adler 2018, allowed us to calculate different values of the emissions of the radiations emitted by the planet. We can see that the emissions the flux is greater without the effect of trees and become smaller due to the cooling effect of trees. From that, we could calculate two main temperatures: the temperature of the planet without the added trillion trees, which is equal to around 14 degrees Celsius, and is very convincing since the average temperature in the 20th century was actually 13.9 degrees Celsius, and the current average temperature in 2020 was slightly above that, which is of course increased due to greenhouse gases. So this result seems to confirm that our model is indeed a good representation of the reality. So this model was then used to calculate the temperature of the Earth upon planting a trillion trees, which would be roughly half a degree decrease, or more precisely 0.43 degrees. This value could then be used into our full model, which is very similar to the albedo model. We've added a one-time effect on the temperature of the trees as a function of the amount of trees that we plant, or the amount of trillion trees we plant. We then added this effect over the course of a couple of years. In this plot, we've added this effect over the course of 15 years. This is an arbitrary value, of course, which doesn't change the outcome, but rather changes the transition period, which could represent, for instance, the amount of time needed to plant trees. This transition period, and during this transition period, we can see a progressive decrease of 0.43 degrees Celsius on the atmospheric temperatures. And after the transition period, the temperature would slowly start rising again. So this model, of course, this graph doesn't take into account any decrease of potential greenhouse gas emissions, but rather just the current predictions.
Now to talk to you a little bit about our extension. So for this extension, we were really trying to find a solution for where to plant trees, and specifically because we saw that with the deserts there's this albedo problem, our initial idea was to plant trees back where we had observed deforestation, so typically like in the Amazon area. However, upon discussing with the other group members, we realized that there may actually be a larger potential for reforestation if we were to change some of our dietary habits. So in this section, we are looking at what would happen if all across the world we stopped our meat and dairy consumption and we essentially became vegan. And we know that this would free up a lot of space on the planet, because currently, and this is part of the data that we searched for, 26% of the planet's surface is dedicated to livestock. So cattle farming, poultry, all sorts of animals that we use as sources of nutrition. And we wanted to see what would happen if we could so stop this dietary habit and use the space that is used up by livestock at the moment as available space for planting trees. And what happens is that if we do this, we get an approximation that we would have space for we would have space to plant a total number of 6.6 trillion trees, which is absolutely huge. So to model this extension, we looked at the potential of planting 6.6 trillion trees instead of 1 trillion trees, and chose the lower bound of 42 gigatons of sequestrated carbon per trillion trees that is estimated by the authors of the paper. And in doing so, we get the following result. We see that we are indeed below 1.5 degrees. In fact, we keep increasing the temperature and reach a maximum just below. And then from 2040 approximately onwards, we have a cooling effect on the planet. And this is extremely interesting and exciting, because we see that something as simple as diets, but also as complex as mindset and habit shifts, can really have a huge impact on what we are experiencing at the moment. So stopping meat and dairy consumption seems like a very solid solution, in fact, to this climate crisis. And not to mention that here we're being very conservative, not only in the amount of carbon sequestrated that we are considering, but we know from studies that show the fact that moving towards a vegan diet have other very beneficial effects on the planet. And just to state one, we know that cows in particular release a lot of methane into the atmosphere. So this is another greenhouse gas that contributes heavily to global warming. So decreasing the amount of cattle ranches that we have would also decrease global warming through the effect of less greenhouse emissions in this world. So that is what we try to achieve here by having a different outlook and explore the endless possibilities, in fact, that we have to move closer to a solution for global warming. And this is just one, and it's a simplified version of modeling it, but it's something that we found extremely interesting to show here.
We then gathered all the results previously found into one convenient interactive model. This model is built around one get function, which gathers the data from all different parts of our project, and then are then used in one manipulate function. As you can see, this manipulate is built around three sliders for the amount of trees, the amount of sequestered carbon, and the rate of emissions by 2050. Three different effects can be selected: the albedo, the vegan lifestyle, as well as the water cycle effect. For instance, if you want to try with roughly 1 trillion trees, we can then see the effect on temperatures depending on how much carbon this trillion tree would store. We can see it decreasing steadily. We can also imagine that we might decrease the rate of greenhouse gas emissions by 2050, which would further decrease this value. We can then consider one of the three effects that we looked at, such as the albedo effect, which, as we can see, would increase the temperature when compared to the version without it. As we know, if we plant a lot of trees in the Sahara, the albedo of the Sahara and the albedo of the planet as a whole would probably decrease, increasing therefore the amount of heat that is trapped from solar radiations. We can also see the effect of vegan lifestyles. The effect of vegan lifestyles, as you've probably seen, is modeled mostly as the amount of space that we would free without the need for agricultural surfaces. Because of that, we can push the slider much further than before and allow for and find enough space on the planet to plant 6.6 trillion trees. As we can see, this would have a dramatic effect on our temperatures. Finally, we can take into account the water cycle effect. As you can see, planting a given amount of trees would have an effect over the course of a couple of years while these trees are planted, and would then remain steadily increasing at the same rate as before. If we increase the amount of trees, of course, this effect would be much more obvious. We can, of course, then try to combine multiple effects, such as the vegan lifestyle and the water cycle effect, which would allow us to plant a big amount of trees and have a tremendous decrease of temperatures, of global temperatures.
So, what is our solution? In summary, 1 trillion trees isn't enough, based on our calculations, and it is true, however, that the modelling and analysis carried out are not fully comprehensive, and that there are many other interesting extension areas that are still left to be examined in future research. Although we would not recommend planting trees specifically in the desert for the previously mentioned reasons, and we would favour reforestation in areas with lower albedo and that are more suited to this kind of transformation, if we really did have to look at planting in the desert, we would choose to plant the Acacia tortilis tree, as it is one that has proven to be most promising for desert greening. Now, besides this, we are aware that it would take a substantial amount of time to plant trees and for them to grow to full size. In fact, on average, it takes 2 people to plant around 3,000 trees per day. And instead, we would recommend implementing the use of drones for planting trees. Yes, you heard me correctly, drones. A company called the Bioengineering Company has designed drones especially for this purpose, and they state that with a team operating 10 drones, they can plant around 400,000 trees in just a day, which hugely increases the efficiency of achieving our mission. In this way, we are using technology to speed up the reforestation process and to find solutions for a more sustainable future. In our opinion, a large part of the solution also resides in conserving the forests we still have. We must stop, or at least slow down, current deforestation. We are currently getting rid of our existing forests at an extremely quick rate, but we know that rebuilding them will take much longer than if we just conserve them now. Not to mention that cutting down forests releases CO2 back into the atmosphere, thus further contributing to warming. The priority of actions would thus be to first conserve the forests we have, secondly rebuild the forests that we have recently cut down. And thirdly, reforest. Lastly, we must be careful about the risks that come with reforestation. Planting trees must not be used as an excuse for avoiding a reduction in greenhouse gas emissions and a change of behaviours. And reforestation is simply not enough, especially if we keep increasing our emissions at higher and higher rates over time. Although we had some promising results from our modelling, we know that in reality it is much more difficult to implement these changes, especially when it requires a worldwide effort and not only depends on one nation alone. We need to make sure that we decrease the amount of carbon in an ecologically and socially responsible way. Thanks for watching this video, and we wish you a happy new year.